What if one telescope opened its eye for the first time and instantly showed us that the universe is far bigger, stranger, and more alive than we were ready to accept? What if the images that just arrived were not only beautiful, but the beginning of a scientific shock that could reshape how we understand everything above us? And before we go further, tap like, subscribe, and share this with the one person in your life who still looks up at the night sky and feels that pull, because this story deserves more than a quick glance. On June 23rd, 2025, a room full of scientists, engineers, journalists, and space fans waited for something they had been chasing for years. Some had spent major parts of their careers helping build the machine behind this moment. Some had written code for it. Some had shaped its mirrors, tested its systems, planned its mission, and defended its cost. They all came for the same reason. They wanted to see whether the wait had been worth it. Then, the first public images from Vera C. Rubin Observatory appeared. And the feeling in that moment was not normal excitement. It was something heavier. Something quieter, because the pictures were not just pretty space photos. They were proof that a new kind of observing power had arrived. In just a short test period, this telescope showed an amount of detail so overwhelming that even experts had to slow down and take it in piece by piece. This is the real reason people are saying the world stopped. Not because the observatory found one single alien signal, one giant exploding star, or one magic answer in a few hours. It was because its first look already made clear that astronomy had entered a new era. The scale was shocking. The speed was shocking, and the deeper message was even bigger. If this is what Rubin can do at the beginning, then the next 10 years may force us to rethink some of the biggest ideas in modern science. To understand why these first images hit so hard, we need to start with the place. Vera Rubin Observatory sits on Cerro Pachon in Chile, high above much of the moisture, light, and atmospheric trouble that distort the sky for telescopes lower down. Astronomers love places like this because the sky is dark, dry, and stable. You want the stars to come in clean. You want the air to get out of the way. You want as little interference as possible between the universe and your instrument. That alone would make Cerro Pachon important. But the mountain is only part of the story. The real star is the observatory itself, and more specifically, the system built to do something no telescope has ever done at this scale. Rubin was designed to scan huge portions of the sky again and again and again, building a living record of change. Most telescopes are famous for staring deep at one target. Rubin is different. It is built to move fast, cover enormous areas, and return often. It is less like a still photographer and more like a cosmic time-lapse machine. At the center of it is an 8.4 meter class telescope and the largest digital camera ever built for astronomy, a 3.2 gigapixel instrument so powerful that a single full image holds more detail than most people can even imagine. When Rubin looks up, it does not merely collect light. It captures an enormous flood of information. Star fields, faint galaxies, dust clouds, asteroids, variable stars, explosions, motion, patterns, differences between one night and the next, little changes that older surveys might miss, fast events that could vanish before slower systems even know where to look. That mission has a name, the Legacy Survey of Space and Time, often shortened to LSST. And the ambition behind that survey is almost hard to say without sounding dramatic. Over roughly 10 years, Rubin is expected to repeatedly map the visible southern sky, building one of the richest data sets in the history of astronomy. Not a snapshot of the universe, but a long, detailed record of how it behaves over time. That matters because the universe is not standing still for us. Stars brighten and fade, asteroids drift, comets appear, supernovae erupt, galaxies collide, black holes feed. Strange objects flash briefly and disappear. If you want to catch a changing universe, you need more than depth. You need rhythm. You need repetition. You need a machine that can return to the same areas again and again with absurd precision. That is what Rubin was built to do. And yet, even with all that expectation, the first public images still felt larger than the promise. One of the early image releases showed the Trifid Nebula and the Lagoon Nebula, regions where gas and dust glow with color and structure, places where stars are born in immense clouds that look soft from a distance, but turn wild and violent when you study them closely. Rubin's image made these areas look alive with texture. Not flat, not decorative, layered, dense, complex. You could sense the shape of the material. You could almost feel the depth. Another early release focused on part of the Virgo cluster, a region crowded with galaxies. Not one or two bright islands in darkness, but a packed field where giant systems, smaller companions, distorted shapes, and distant background objects all seemed to coexist in one impossible scene. The deeper people looked, the more they saw. Nearby stars from our own galaxy sat in front. Massive galaxies hung farther out. Tiny dim systems whispered from deeper space. It was like opening a door and realizing there were 10 more rooms behind it. And this is where the story becomes almost unbelievable. The Observatory S team explained that in a short early observing period, using only a fraction of what the full camera can capture, Rubin recorded millions upon millions of galaxies and stars, along with thousands of asteroids. Some of those moving objects had never been cataloged before. Think about that for a second. Before the main 10-year survey had truly even settled into its full work, the observatory was already pulling previously unknown objects out of the dark. This is why the first images did not feel like a normal opening act. They felt like a warning shot from the future, because astronomy has had powerful telescopes before. It has had beautiful space pictures before, it has had big survey projects before, but Rubin is combining width, speed, repetition, and digital scale in a way that changes the kind of questions scientists can ask. It is not just about seeing farther. It is about seeing more, seeing sooner, and seeing change with enough consistency that hidden patterns begin to reveal themselves. That could matter for practical reasons almost immediately. One of Rubin's major expected strengths is finding asteroids, especially objects that move through the inner solar system. It might matter for planetary defense. Many dangerous objects are not noticed because they are small, faint, moving, or simply lost in the enormous amount of sky we have to watch. Rubin S repeated, scans can help change that. It can spot motion. It can compare nights. It can flag what was not there before. In time, that may make it one of the most valuable tools humanity has ever built for finding potentially hazardous near-Earth objects. But asteroid hunting, important as it is still only one chapter in a much larger story. The deeper purpose of Rubin goes back to the woman whose name it carries. Vera Rubin was one of the astronomers who helped expose one of the greatest mysteries in science. When she studied how galaxies rotate, she found something deeply strange. The stars near the outer parts of galaxies were moving too fast. Based only on the visible matter in those galaxies, the outer stars should not have been held so tightly. They should have drifted away. But they did not. The math did not match the light. That gap led to one of the strongest lines of evidence for dark matter, the invisible mass that seems to shape galaxies, and larger cosmic structures through gravity even though we do not see it directly. Dark matter is one of those ideas that feels almost fictional the first time you hear it. Something massive, something influential, something everywhere, and yet invisible. We know it by what it does, not by what it looks like. If that were the only mystery, it would already be huge. But modern cosmology carries another one, dark energy, the unknown driver, behind the accelerating expansion of the universe. Together, dark matter and dark energy appear to dominate the cosmic budget. Ordinary matter, the stuff that makes stars, planets, oceans, trees, bodies, and buildings, is only a small fraction of the whole. So imagine the scale of the question Rubin Observatory is stepping into. We're not talking about polishing one detail in a nearly completed picture. We are talking about investigating the invisible framework of the universe and the unknown force affecting its expansion. That is not a side quest in astronomy. That is the main event. Rubin will not directly photograph a dark matter particle floating in space. That is not how this works. Instead, it will gather the kind of data that lets scientists infer the shape of the invisible. By mapping the distribution of galaxies across enormous volumes of space and tracking how matter bends light through gravity. Astronomers can test models of how dark matter is arranged and how cosmic structure grows over time. The same goes for dark energy. If the universe is expanding in a particular way, and if that behavior changes over cosmic time, then huge sky surveys help. You need massive samples. You need consistency. You need the ability to compare one part of the sky with another and one era of cosmic history with another. Rubin was built for exactly that kind of patient, large-scale statistical truth hunting. And that is why the first images mattered beyond their beauty. Every glowing point, every smeared galaxy, every measured position, brightness change, and motion trace becomes part of a much larger machine for understanding reality. Beauty gets the headlines. Data changes the textbooks. If this story is already pulling you in, hit like, subscribe, and send this video to one person who still feels something. When they hear the word universe, because the deeper we go, the more unreal this becomes. Now here is where the emotional power of the moment really starts to build. For the public, the first images felt sudden. A dramatic release, a fresh wave of headlines, a flood of clips and reactions. But for the people behind the observatory, this was the end of a long road. Rubin was not built overnight. Projects like this move through years of design, engineering, funding battles, testing, delays, software development, and coordination across institutions. The mirror system must work. The camera must work. The data pipeline must work. The mountaintop infrastructure must work. The scheduling must work. The calibration must work. The alerts must work. Because once the real survey begins, the observatory does not just need to take pictures. It needs to process a torrent of information and share useful results quickly enough for action. That last part is easy to underestimate. Rubin is not valuable only because it sees a lot. It is valuable because it can turn observation into action. If the telescope notices something that changed, such as a transient flash or a moving object, the system can help alert the scientific community. Other observatories can respond. Different instruments can point. Spectra can be taken. Follow-up measurements can begin. In astronomy, timing matters. Sometimes the difference between a historic discovery and missed opportunity is hours. So when the first images landed, they were showing more than the power of a telescope. They were showing the beginning of a giant scientific network coming alive. And the public response made sense. People kept saying the same thing in different words. How can one image contain so much? How is this real? Why does it feel like the sky suddenly became crowded? The answer is simple. The sky was always crowded. We were the ones with limited eyes. That is one of the most humbling patterns in science. Again and again, reality turns out not to be small, clean, and obvious. It turns out to be layered beyond expectation. The more sensitive our tools become, the less empty the universe looks. Darkness becomes structure. Blank space becomes hidden population. Silence becomes signal. That is exactly what Rubin's first images did to people. They turned abstract numbers into emotional evidence. Millions of galaxies is a phrase you can hear and forget. But when you understand that a tiny patch of sky can hold more systems than your mind can comfortably picture, the universe stops being a concept. It becomes weight. It becomes scale. It becomes almost uncomfortable in its size. And there's another reason this moment hit so hard. Rubin's design means that what we saw first is not the full story. The debut images were a beginning, not a peak, a sample, not the archive, a doorway, not the building. That creates a strange kind of tension. On one hand, scientists are excited because the instrument clearly works at a remarkable level. On the other hand, that same success raises the pressure immediately, because now the question is no longer whether Rubin can see. The question is what Rubin will reveal once it starts doing this over and over for years. That future is where the real scientific drama lives. For decades, cosmologists have been building models that explain the large-scale behavior of the universe with incredible success. These models are powerful. They are not random guesses. They are based on measurements, predictions, and cross-checks from many different methods. But there have also been tensions, mismatches, and uncomfortable hints. Sometimes the universe agrees beautifully with our equations. Sometimes it gives us just enough friction to remind us our understanding is incomplete. One of the most fascinating possibilities is that deeper, cleaner data might not simply sharpen old answers. It might expose where the old framework bends. That is especially important when people talk about dark energy. In the standard view, dark energy is often treated as something constant, a background property that drives expansion in a stable way. But what if that assumption is too simple? What if the effect changes over time? What if the strength is not truly fixed? What if our model works well enough for now but starts to crack under better evidence? To be clear, scientists are careful here, and they should be. Extraordinary claims do not become true because they sound exciting in a thumbnail. A new telescope does not overturn decades of cosmology in its first week. Anyone telling you the mystery is already solved is getting ahead of the evidence. But the reason Rubin matters so much is that it gives researchers one of the best opportunities ever created to test these ideas with far greater statistical power. That means two truths can exist at the same time. Truth number one. The first images are not, by themselves, proof that dark energy is changing or that physics is broken. Truth number two. The first images are proof that a machine now exists that is unusually well suited to helping us find out. That distinction matters. It protects us from hype while preserving the real wonder of the moment, because the honest story is already dramatic enough. Human beings climbed a mountain, built an instrument of staggering precision, taught it to process a huge river of light, and on one of its first public outings, it delivered images so rich that scientists could begin asking some of the biggest questions in existence with renewed force. You do not need fake exaggeration when the real event is this powerful. And there is something else hidden in the public reaction that I think matters. People were not just impressed by the pictures, they were moved by what the pictures represented. In a time when attention is fractured and everything competes with everything, a telescope still managed to stop people for a moment and make them feel small in the best possible way. That is rare. It reminds us that wonder is not childish. Wonder is a serious response to reality when reality is big enough. Rubin's first images did that. They cut through noise. They made people pause. They made them ask questions. And maybe that is part of why the release spread so fast. It was not only science news, it was emotional news. It told millions of people that the universe still contains genuine surprise. But surprise alone is not the end of the story. Rubin's long mission could affect several areas of science at once. First, there is the inventory problem. We still do not know everything moving through our own solar system. Rubin can help discover asteroids, comets, and perhaps unusual visitors crossing our neighborhood. Catching these objects earlier and more often means better orbit calculations, better warnings, and better science. Second, there is the transient universe, the sky of sudden events. Stars explode, black holes tear matter apart, unusual flares appear, some events fade fast. Rubin S repeated observations can help create a more complete census of these changes and give other observatories a chance to investigate them before the trail goes cold. Third, there's galactic structure and evolution. With so many galaxies observed at such scale, astronomers can study how galaxies form, cluster, merge, and grow under the influence of visible and invisible matter. Patterns that were once buried in too little data may start to emerge cleanly. Fourth, and perhaps most famous, there's the dark sector of the universe. The large-scale map Rubin will help build could become one of the strongest tests yet of how matter is distributed. That is an astonishing amount for one observatory to carry. And yet, somehow, the first images made it feel possible. What I find especially powerful is the contrast between the emotional tone of the release and the scientific discipline behind it. The images invite awe, but the researchers do not get to live on awe alone. They have to calibrate, verify, compare, model, publish, challenge, and repeat. The public sees wonder in a frame. The scientists then spend years turning that wonder into reliable knowledge. That is the harder part. And in a way, it is the more beautiful part too. Because science is not just the flash of discovery. It is the discipline of not lying to yourself about what you have found. It is resisting the temptation to jump to conclusions. It is accepting that the universe does not owe us quick answers just because we built a clever machine. Rubin S' first images were a spectacular opening. But what gives them real weight is the slow work that follows. That slow work may be where the biggest breakthroughs hide. And if you want more stories, where one image can shake an old idea, do something simple right now. Like this video, subscribe, and share it with one person who loves the unknown. Think about the numbers involved. Millions of galaxies in early combined views. Thousands of asteroids detected. A camera so large that even looking at the full richness of a single capture is a challenge. A survey planned to run for a decade, night after night, season after season, year after year. There is something almost relentless about it. Rubin is not making one heroic leap. It is building an argument over time. And strong arguments change science. If the observatory keeps delivering as expected, it will not persuade by drama alone. It will persuade by accumulation. More measurements, more consistency, more comparison points, more opportunities for one suspicious pattern to either vanish under scrutiny or survive it. That is how deep scientific change usually happens. Not all at once, and not because one headline demanded it. It happens when repeated evidence becomes too strong to ignore. This is why Rubin S' first images felt like more than a debut. They felt like the opening move in a very long game. Now let S talk about the psychological side of this, because it matters for understanding why people reacted so intensely. Human beings are strange with scale. We can hear a big number and not feel it. 10 million galaxies sounds huge, but unless your mind connects it to something visual, it stays abstract. Rubin changed that by giving the number texture. Suddenly the idea was not just that the universe contains many galaxies, it was that a machine on Earth could reveal a staggering crowd of them. That turns a statistic into an experience. And when an experience lands deeply enough, it changes how people think. The night sky is familiar to us. We have lived under it forever. We name constellations. We tell stories about stars. We act as if the sky is a settled thing. Then a new image arrives and reminds us that our familiar sky is only the thin surface of reality. What felt calm turns out to be overflowing. There is a philosophical punch in that. It suggests that mystery does not disappear when science advances. Very often, science increases mystery. Rubin does not close the book on the universe. It opens new chapters faster. That may end up being one of its greatest gifts to the public. Not just answers, but a renewed relationship with the unknown. And the unknown is everywhere in this story. Unknown objects moving through the solar system, unknown patterns in galaxy clustering, unknown details in how matter bends light, unknown behavior in cosmic expansion, unknown rare events waiting to flare for a few hours and vanish, unknown structures hiding in data too large for a person to fully absorb at once. There is almost something poetic about that. A telescope, named after a scientist who helped reveal invisible matter, is now beginning a mission built around exposing hidden structure. The symbolism is powerful, but it also happens to be real science. And that matters because some stories are so cinematic that people assume they must be oversold. This one does not need help. The facts are already enough. A mountaintop observatory in Chile, a giant survey telescope, the largest astronomical digital camera, first public images that stunned experts and the public alike, a 10-year mission to repeatedly scan the sky, a link to the dark matter mystery through Vera Rubin's legacy, the possibility of discoveries ranging from asteroids to cosmology. That is not marketing copy. That is the actual setup. Still, the most responsible way to tell this story is to keep one foot on the ground. So let S do that. The first images are not the same as final scientific conclusions. They are proof of capability. They are a demonstration that the instrument can deliver exceptional data. They are an opening chapter that hints at what is coming, not a full answer to the hardest questions. This matters because public excitement can sometimes blur the line between observation and explanation. Rubin S real test will come over time. Can it maintain consistency? Can it deliver the expected survey depth and cadence? Can its measurements help resolve major tensions in cosmology? Can it transform transient astronomy by catching events quickly enough and often enough? Can it dramatically improve the catalog of small bodies in the solar system? Can it help us map the invisible scaffolding that shapes galaxies and clusters? Those are the questions that will define its legacy. But even that framing should not make the event feel smaller. In fact, I would argue the restraint makes it more impressive. Because if scientists are this excited while still being disciplined, you know the underlying machine must be extraordinary. A lot of the loudest moments in public science vanish quickly. A headline explodes, then fades, then gets replaced by the next wave. Rubin has the chance to do something rarer. It can stay relevant. It can keep producing moments. It can keep feeding both public imagination and scientific work year after year. That means the first images may end up being remembered for how prophetic they felt. They may be the beginning of a decade in which the night sky becomes more dynamic, more crowded, and more informative than most people ever realized. If that happens, June 23rd will be remembered as one of those threshold moments, the kind where you can look back and say, that was when the conversation changed. Here is another reason I think this matters so much. Science often advances in two different rhythms. There is the fast rhythm of public release, reaction, and headline. Then there is the slow rhythm of careful accumulation. Rubin may be one of the rare projects that dominates both. It can create breathtaking visual moments that spread instantly and at the same time build a deep long-term record. That combination is powerful because it keeps the public emotionally connected while the science matures. People do not just want to hear that data exists. They want to feel why it matters. They want a reason to care before the full papers arrive. Rubin gives them that reason. It translates extreme technical capability into visible evidence. It lets people see the beginning of the process. That is why the first images did more than impress. They recruited attention for the long game. And that long game could surprise us in ways we are not even predicting yet. Every major observing tool is built with expected science goals. But history shows that some of the most important discoveries come from the unexpected. The thing you were not aiming at, the pattern you did not think to look for, the object that should not be there, the mismatch between prediction and measurement that refuses to go away. Rubin is exceptionally well placed for that kind of surprise because it is not narrowly focused on one kind of target. It is scanning broadly and repeatedly. That means it can catch the unusual by comparison, the odd motion, the unexplained flare, the statistical outlier that keeps repeating, the rare event that becomes visible because you have sky coverage. In other words, some of Rubin-esque greatest discoveries may be the ones no press release is currently promising. That possibility should give you chills. Because somewhere in those future observations may be an object, a pattern, or a deviation that shifts an entire field. Not because we wanted drama, but because the universe really is stranger. So if you are still here, take 5 seconds and do one quick thing. Like this video, subscribe to the channel, and share it with someone who loves standing at the edge of a mystery. Let S zoom back out and see the whole emotional shape of this story. A scientist spends years studying galaxies and notices that the visible matter is not enough. That clue becomes one of the foundations for the dark matter problem. Decades later, an observatory named in her honor is built to scan the sky at immense scale to help us study the invisible forces and structures shaping the cosmos. After years of work, the instrument finally reveals its first public images. Those images immediately show a level of richness and depth that confirms the machine is not ordinary. And now the world waits to see what repeated observation will uncover. That is a beautiful arc. Not neat, not finished, but beautiful. It is also a reminder that science is one of humanity's longest conversations. Vera Rubin did not solve every mystery. The people building this observatory are not expecting to solve every mystery in a week. Knowledge moves across generations. One person notices the problem. Another builds a better tool. Another tests a harder idea. Another inherits the data and sees what the previous generation could not. Rubin Observatory belongs to that chain, and I think there is something deeply moving in the fact that the chain continues through images. Light that traveled for millions or billions of years reaches a mountaintop in Chile. It gets captured by human-built sensors, processed by human-written systems, and then appears on screens around the world where people stop and stare. Across time, distance, and engineering, the universe enters our shared awareness. No wonder the reaction felt so intense. You were not looking at just another picture. You were looking at evidence of a new way of paying attention. And paying attention matters because the universe does not become simpler when ignored. It keeps moving. It keeps expanding. It keeps colliding, flashing, bending, and drifting. Rubin increases the odds that we will notice. That alone makes it historic. There's also a quieter lesson here about patience. We live in a culture trained to expect instant meaning. Immediate verdicts, quick takeaways. Rubin pushes in the opposite direction. It gives us a thrilling beginning, then asks us to commit to years of observation and careful interpretation. It says, in effect, if you really want to know what the universe is doing, you must be willing to watch for a long time. That is a powerful message, and it is probably the right one, because the biggest truths are often not hiding behind one dramatic frame. They are hiding in patterns too large, too slow, or too subtle for rushed attention. Rubin was built for pattern hunting. It can collect the repeated evidence needed to sort noise from structure, coincidence from law, and hype from discovery. If you care about truth, that should excite you. And if you care about wonder, it should excite you even more. Because there's nothing cold about this kind of science. It is disciplined, yes. Careful, yes. But it is driven by an old human impulse. We want to know where we are. We want to know what the universe is made of. We want to know whether the strange behavior we measure is pointing to hidden matter or hidden flaws in our theories. We want to know whether the sky is as static as it seems, or whether it is alive with changes we have only just learned how to track. Rubin steps directly into those questions, and it does so at a scale that feels worthy of them. So when people say the first images stopped the world, I think what they really mean is this. For a brief moment, a new instrument forced us to feel both our smallness and our reach at the same time. Small, because the universe it revealed is overwhelming. Reaching, because we are capable of building tools that can face that scale, and still extract meaning from it. That combination is one of the most human things I can imagine. We are tiny compared with the cosmos, and still we measure. We are brief, and still we plan surveys. We are fragile, and still we climb mountains to catch light from distances that crush the imagination. We do not win against the size of the universe. We answer it with curiosity. That is what these images really captured. Not only distant galaxies and glowing nebulae, but a portrait of human ambition meeting cosmic mystery without blinking. And the most thrilling part is that this story has barely started. Somewhere in the years ahead, Rubin may help reveal asteroids we have never seen and exploding stars we would have missed. Patterns in galaxy distribution we do not yet understand, and maybe even clues that transform our ideas about dark matter and dark energy. Not every result will be dramatic. Some will be technical. Some will be incremental. Some will be contested. That is how real science works. But somewhere in that flow of data, there may also be moments that feel like a crack opening in the wall, a result too strong to dismiss, a pattern too clean to ignore, a discovery that changes not just a field, but the questions the field asks next. That is why this opening matters. It is not because the mystery is over. It is because the machine built to chase the mystery has finally begun. And once you understand that, the first images stop looking like a finish line. They start looking like a signal fire. A bright announcement from a dark mountain saying that the next decade of astronomy may be unlike anything we have seen before. Maybe that is why the room went quiet. Maybe that is why so many people stared. Maybe that's why the images spread so fast. Because deep down we all recognize the same thing. We had just watched the universe become larger in the human mind. Not larger because space itself changed, but larger because our ability to witness it took a leap forward. The hidden became more visible. The distant became more crowded. The future of discovery became more real. And that is a rare kind of moment, the kind you remember years later. Not because one answer arrived, but because a door opened and everyone could feel that the room beyond it was enormous. So here is the truth that will stay with me. The first images from Vera Rubin Observatory did not stop the world because they solved the universe. They stopped the world because they reminded us how unsolved the universe still is. And then handed us a powerful new way to keep asking. That may be even better than an answer. Because answers close questions. A machine like this opens them wider. And somewhere in the flood of light still coming, in the repeated scans, the moving dots, the subtle distortions, the rising curves, the vanishing flashes, the crowded fields, and the depth, the next great shift in our understanding may already be waiting. The observatory has opened its eye. Now it is our turn to keep looking.